started discussing laws of conservation, right? And again, so what's the point? Yeah, we at this point we know how we can write all equations of motions with these constraints, with those constraints, without constraints, pretty much almost all possible situations, right? And of course, solving those equations of motions can be quite challenging sometimes, right? And of course, if you cannot, for example, solve the differential equation, right, equation of motion, you can at least get some information about motion of the system by analyzing the laws of conservation, right? So that's why we basically, okay, now diving into this world to get some information in case of troubles, right? Because it's also very, very useful, right? So in the previous class, I sort of started introducing some basic stuff, right? But we haven't finished it. So basically here we finished at the previous class. So I just wrote down the typical Lagrange equation for a conservative system, right? And reminded, so if Lagrangian doesn't depend explicitly on one of the coordinates, then that coordinate is called cyclic or ignorable. Some people pronounce it cyclic, but I like cyclic. Cyclic sounds like sick, right? That's the only reason why. All right, and as a result, of course, this generalized force is 0, and of course, as a result, this generalized momentum is conserved, is constant, right? As a result, generalized momentum is conserved, right? And now two possible situations. And again, that's where we stop. So if this generalized coordinate is, which way I wrote it? Okay, yeah, is some translational coordinate like x, y, z, translational coordinate. Then, of course, this generalized momentum is a linear momentum. Right? So in this case, generalized momentum is a linear momentum. Right. And the second situation, and of course, yeah, linear momentum is conserved, of course, right? And if this generalized coordinate is some angular coordinate, like phi, theta, something else, right? Then, of course, this generalized momentum is an angular momentum. And of course, in case of if this coordinate is ignorable, of course, that angular momentum is a constant of motion, is conserved, right? Okay, so so after this, I promised you that we will go and start connecting properties of space and time with laws of conservation. But I decided to digress a little bit, all right? In order to, I haven't posted the second homework yet, right? But tonight definitely, because yesterday I didn't have time to sit and think through. There will be one problem. There will be some cylindrical surface and or spherical, I don't remember, and there's another cylinder rolling on that on that cylindrical surface, and you will have to find something, right? And there's one place for typical mistakes, right? So I wanted to address that. I think some of you were in my undergraduate level course, and I think I discussed that, right? And so now I just want to sort of repeat that, because it's a, as I said, a place where many students make mistakes. Okay, so let me do this again. Sort of, it's a, I will write. Let's digress, and then we will get back to the laws of conservation, right? So let's digress. Right? Digression to help with the homework too. So what if, well, let's assume that we have some cylindrical, or not spherical, cylindrical surface. It doesn't matter, because we're going to basically look at a problem in two-dimensional space, right? So let's assume that we have this cylindrical or spherical surface. right? Okay, something like this. And the center of that sphere is here, right? Okay, let me draw. So let's say this is radius. Let's say radius is b, and the inside of this surface, of course, this surface is stationary. There is a disc, hoop, cylinder, no ball. It doesn't matter, right? Is rolling. So let's assume it's this of radius a, right? Of course, rolling without slipping. Okay, so now let's displace it. And again, my goal is, of course, to write the Lagrangian. But actually, potential energy here, it will be straightforward. I want to discuss kinetic energy, how we can write down kinetic energy for a case like this. Okay, so now let me displace, of course, position of this, displace this disk or whatever this object. Let me do it like this. So let's say this will be a new point of contact, and the object is here, right? Okay, so I displaced it. Of course, kinetic energy, you know, before I start even talking about kinetic energy, of course, let me show the no slipping condition on the diagram, right? Of course, so right now the point of contact is here. So let's say this is the moment of time t larger than 0, and this is the moment of time t equals 0. So at t equals 0, this was our point of contact. And of course, after displacing the object, the point of contact will be somewhere maybe over here, right? So this point will move over there. As a result, this arc length must be equal to that arc length. Basically, that is the no slipping constraints on a diagram, drawn on the diagram, right? Okay. And of course, now kinetic energy. So of course, kinetic energy will consist of two parts. Kinetic energy, translational kinetic energy describing the motion of the center of mass. So which will be, okay, maybe I will write TCM plus T rotational. And of course, T of center of mass, we can, we should be able to easily write. So it's a m over 2. Let's assume mass of that object is m. And then, of course, we will have to introduce the first angle, angle theta, which will define position of the center of mass of this. Okay, let me call it disk. So let me introduce, of course, this angle theta. Right? So using that angle, we should be able to, of course, this is the trajectory of this center of mass, right? And so it will be, this distance will be b, distance from this to this point, it will be b minus a squared times theta dot squared. That will be, of course, kinetic energy. I don't think that I have to convince you in that. So it will be b minus a squared times theta dot squared. So it's a kinetic energy describing the motion of the center of mass. And now this rotational kinetic energy, of course, about the center of mass, right? Okay, so let me write first. Of course, it will be 1 over 2. Some moment of inertia. Of course, it depends on the object. Ball, disc, hoop. It doesn't matter. All right, and some new variable phi dot squared. Okay, so now we're going to talk about this phi. Which phi can be used or must be used? Yeah, probably must be used. Okay, usually, okay, even before, look, so this is kinetic energy, right? If you look at the derivation of this rotational kinetic energy, it's a kinetic energy over pure rotational motion about the center of mass. Nothing else should be there. Only rotational motion about the center of mass. And now, so what can, let me put phi and question mark. Usually, students use this angle. Don't draw it. Usually students use this angle. And they call this is as phi. We will erase it. But usually that's the choice of the students, right? So now let's discuss. Will it work? So let's start. Let's look at the simplest possible situation. Let's remove this cylindrical surface, right? Let's assume that there is no translational motion. So let's first look at just a disk spinning around a fixed axle. So axis of rotation goes through the center and no translational motion. In order to understand, I'm just going into this in order to understand what do we have to do about this angle phi, right? So, so this axis is fixed. Let's look at this. And of course, how do we usually describe orientation of this disk? So you would usually pick some stationary, well-defined direction. It can be, for example, horizontal, right, or maybe this way. But let me pick this direction. Okay, maybe I will use solid line, right? So let's say this is a fixed direction. Right? And then, of course, we can pick some point. At the initial moment of time, that point was probably here. And then at the moment of time t, it moved, okay, rotated to this point. And then, of course, we can introduce angle phi. Okay, I don't like this, right? And of course, we can introduce angle phi. Okay, and of course, we can write kinetic energy in this form, right? 1/2 I phi dot squared. It worked. No troubles here. We have a pure rotational motion about the center of mass. Nothing is involved. Nothing else is involved. Now let's look at slightly more complicated situation. What if we make this disk rolling on a horizontal surface? Let's say horizontal surface, and let's say first this disk was here. Let's say this is at t equals 0, and then at t larger than 0, let's say this disk is somewhere up here. Right, so it gets displaced. Right. And so this is the point of contact, this is the point of contact. And usually, how do we usually describe orientation of this disk in this case? We would usually draw a well-defined direction which goes through the center, through the point of contact, right? So at t equals 0, this was the point of contact. And then at t larger than 0, of course, that point of contact will move, for example, to that point, right? So, and as a result, of course, we usually measure the angle phi from that fixed, well-defined direction, vertical direction. Maybe I should use sort of like this green. Okay, so that's our direction from which we measure angle. So in this case, again, there is only rotational motion about the center of mass involved. Yeah, we have translational motion of the direction, but it doesn't contaminate the rotational motion about the center of mass. In this case, we have only pure rotational motion about the center of mass. Right? And every time direction is fixed, from which angle is measured. Now let's go back to our situation. Right? So here no troubles using 1/2 I and this phi dot squared. Now let's look at our case. So if we measure angle phi, like here, force of habit, which from the line which goes through the point of contact, and very often students, that's what students do. Okay, so this, if we try to measure angle phi this way. So now let's displace even maybe more of this. So if a point of contact here, and look what happens with the direction from which we measure angle. So first direction is this way. Now if we displace it even more, direction will be different. Direction from which we want to measure angle phi changes. Direction is this direction is also rotating. It's basically like a running away from you, not from you, from from this point which we use to define orientation of this disk. It's sort of like a situation if you try to measure, for example, velocity of, I don't know, of a car, and let's say this is your origin, right? And your origin is running away in the opposite direction. Usually we measure velocity of the object, of the car, right, relative to a stationary origin. So origin is stationary, and we can define position of the object and velocity of the object, and that will be velocity only of that object. Nothing else will contaminate it. But in this case, the direction is also spinning, is also rotating. It's sort of like if the origin, which we use to define position of the car, is also moving. So it shouldn't be like this. Your origin shouldn't be running away. In this case, direction from which we measure angle phi shouldn't be running away. But now it is. You see again. If you again displace it more, so here direction from which we measure angle phi is this, and then the direction will be different. No, it's in a second you will see that this rotation contaminates that. Okay, so you see this, the way we choose angle phi right now is not a good way. So we need to choose a well-defined direction. For example, let's pick a vertical direction. So now I can change this. So let me erase this. Right. So now I can pick this direction, well-defined. It doesn't spin because I decided to measure it this way. And now angle phi should be defined this way. So this is the angle phi. Now we have only rotational motion about the center of mass. Nothing else will be involved in this. Because again, in this expression, we assume that we have only rotational motion about the center of mass, nothing else. But here, okay, so if we define angle phi this way, then what is this angle? It's a theta. It's angle theta, which basically describes how fast this direction is spinning, which we were talking about just a few minutes ago, right? So basically this theta dot would be involved in our in this term if we used original way of measuring phi, right, which shouldn't be. All right. So this rotation shouldn't affect, shouldn't be shouldn't be in the definition of angle phi, right? Shouldn't be in the definition of angle phi. Right? So that's the problem. How we should measure angle phi. Right? So don't measure it from the direction which goes through the point of contact in this case. Because the point of contact, okay, this direction is by itself also turning all the time. And of course, that rotation is described by theta dot. Okay, so and now probably I will also write, it's a pure rotation about cm. Nothing else must be also there, right? Okay, so now actually equation of constraints, no slipping conditions. Now we should be able to write that easily, right? So I'm running out of space, probably I will write on top. So now I can write no slipping condition. So no slipping condition. On the picture it's already shown, so it's this arc length must be equal to that arc length. So this arc length can be written as b times theta equals, and then this arc length over smaller radius, it should be what, a and phi plus theta, a times phi plus theta, a times phi plus theta. So that's no slipping condition. Maybe I can also show that this direction is rotating, sort of like running away from us, running away, right? Okay, so I wanted to digress and discuss this because you will need it. There will be a problem, as I said, about cylinder on top of cylindrical surface, and you will have to find, I think, normal force and the friction, all right, forces of constraints, right? And that's the, of course, everything will be, instead of concave surface, you're going to have a convex surface, but idea is here, right? How to introduce the correct angle, which would describe only pure rotational motion about the center of mass. Okay. And of course, yeah, tonight I will post the second homework. After the first qualifier exam, we're going to have oral qualifier exam today. All right. And so now back to laws of conservation. I will erase that in a second. And first, let's discuss conservation of linear momentum, as I said, right? Spatial homogeneity and conservation of linear momentum. Right. Okay, let me write that down. So now, spatial homogeneity and conservation of linear momentum. Again, I explained at the end of the previous class, what does it mean, space homogeneous in a certain direction? Let me just quickly repeat. Let's say this is the direction along we think the space is homogeneous. So what happens with the system? So if you have certain system, for example, at this point, right, and if you let it live, there will be some life. But at the same time, if you freeze the system so that conditions will be exactly the same, right? So velocities, forces, right? Everything is the same. So basically freeze it, displace it in this direction, unfreeze it so that conditions of the same system here and there exactly the same, identical, except for they're displaced. And let them live, life would be exactly the same of both systems. You wouldn't be able to tell the difference between life of this system and life at that system. By life, I mean basically motion of the system will be exactly the same. So in this case, we can say, yeah, that space in this direction is homogeneous, right? And again, what does it mean life is the same? Okay, yeah, life is the same, it means motion the same. Yeah, I mean, of course, since Lagrangian describes everything about the system, right? So it means that if equation of motion of that system and this system exactly the same, it means that Lagrangian of the system over there and over here must be exactly the same, right? So we're going to look at the change in the Lagrangian, basically variation of the Lagrangian between these two systems. And of course, we're going to equate them, that variation to 0, because again, as I said, Lagrangian here and Lagrangian of the system over there must be the same, right? So, and from there, we will extract conservation of linear momentum, right? So the first described in general in words, and now let's Let's derive it actually. Let's show. So let's assume that we have a system, some system of n particles. Right, oops, particles. And Lagrangian, which describes it, it's a L of qi dot and t, right? And let's assume that q, which way I label it qi. Okay, some qi is translational coordinate, right? It's like here I wrote it. X, Y, Z, right? Translational coordinates, and here angular coordinates. So we're talking about this translational, right? Or maybe I can draw some picture, maybe, right? So let's say this is our that direction along which we think a space is homogeneous. So it's a qi, and the system first it will be somewhere over here. The system of n particles. Feel like two eyes and mouth, right? Okay, and of course we can displace it. And again, which displacement we have to use? Of course, virtual displacement, because you remember what are the conditions when you do virtual displacement? You basically freeze the system. Time is frozen, velocities are frozen, everything is frozen except you just change position. That's the idea of virtual displacement, right? And that's what we want to see here. We want to see the life of the system at this point and that point under exactly the same conditions, right? Right. So, and okay, it's basically the same system, right? But of course I cannot draw exactly the same. And right, so we're going to displace it, and that displacement will be exactly the same for all particles. Because again, you remember, you freeze the system, so the particles are frozen, and then you just make a translational displacement. So all the particles are going to be displaced by exactly the same, displacement. So which we're going to call delta qi, right? So delta qi, and that will be some constant, right? Constant for all particles, right? And so, as I said, also I should probably write. So, same L. Of course, there must be eventually same L. We're going to use that fact. Now I just want to state it at the very beginning, and at a certain point, we're going to use that. All right. So now let's just look at dl. And then, of course, we will make a transition to virtual displacement. We'll start first with dl and then apply conditions in order to switch to a virtual displacement. All right, so L depends on this. So summation, I use which index? I. Okay. I from 1 to n, partial derivative of L with respect to qi, and dqi, then plus summation out of dl with respect to qi dot and dqi dot, and I'm running out of space, plus partial derivative of L with respect to time, right? Dt. Okay, and as I said now, switch to a virtual displacement. And again, it's very important because, again, we want to freeze the system so that the conditions will be exactly the same. Conditions here, conditions there, and that's what virtual displacement gives us. Okay, so in the virtual displacement, of course, dqi will be switched to delta qi. Then, d change in the velocity. There wouldn't be any changes in the velocity. Because again, if our velocity was that way, for example, for this particle, you freeze the system, displaced it, it will be exactly the same velocity. Of course, if we rotated the system, like in the next step, if we would discuss isotropy of space, of course velocity would be different, right, upon rotation. But since it's just a translational motion, velocity will be exactly the same. So dqi dot will give us 0, right? So which way I wrote it? So then will be dqi dot will go to 0. And of course dt, change in time, is 0 because, yeah, that's the essential condition of the virtual displacement. We freeze the time. So as a result, all the conditions are frozen and we just change position. And of course dt also 0. So this and these two last terms will disappear, right? So this will go to 0, and of course this will go to 0. As a result, delta L will be equal summation partial derivative of L with respect to Qi delta Qi. And now it's time to use that fact. Since this direction is space in that direction is homogeneous, it means that life of the system here, life of the system there must be the same. Any life is explained by the Lagrangian. It means that L here and L there must be the same, and delta L, variation of L, must be 0. So now it's time to apply homogeneity. Okay, so let me write. So if, which way I wrote, if the space is homogeneous, right? L does not change. Does not change. So it means that L is invariant. L is invariant. Right? So we can write as a result, delta L must be equal to 0. So as a result, I can step up and put here equals to 0. So as a result, I can apply this. Okay, so now this delta Qi, it's exactly the same for all particles. Here, summation over all system over all particles. So we can take this delta Qi, it's some constant, some epsilon, and take it outside of the sum. Right, so this is some epsilon, some constant. So we can take it outside of the summation here, summation over the whole system. Right, so it will be some epsilon and summation, partial derivative of L with respect to Qi, and equals to 0. Of course, this can be dropped. It's a constant, exactly the same. So we can drop it. Actually, not drop it, just cancel it. Right? Now, let's use Lagrange equation. I need to invade this part of the board. So probably I will write it here. So let's use the fact that dl over dqi, of course, equals to the total time derivative out of dl over dqi dot. Soon I will have to change the marker. It's getting too, giving less and less contrast. Right. So we'll plug it. So we'll have summation, of course, over the whole system, d over dt, and partial derivative with respect to qi dot equals to 0. Right. Okay. Time derivative can be taken outside. Oh, outside of the sum of summation, right? So of course we can write it as d over dt and then summation over the whole system out of this partial derivative, and it must be equal to 0. So that dl over dq I dot Of course, in general, of course, it's just a generalized momentum. But since we assume qi is a translational coordinate, of course, it's that derivative, this derivative, is our linear momentum, just a linear momentum of one particle. But then since we're going to sum over the whole system, of course, this whole thing is going to give us total linear momentum of the system. Right. Let me write, so dl over dqi dot, it's just a pi lin mom of, okay, I particle. And then, of course, this whole thing is going to give us total linear momentum of the system. So, and then, of course, maybe I will write here as well. So summation over, okay, p I, it will be total linear momentum of the system. Should I use the vector form? No, just like this. So it's a total linear momentum of the system, right? So as a result, we're getting that dp over dt, right, equals to 0. And of course, as a result, linear momentum is constant. No, I'm thinking, standing and thinking, because it will be a component of a linear momentum. So that's why I'm standing and thinking. I need to add, right? So still subscript I, right? It's a component of the total linear momentum along that direction, right? Right. So pi of the total, right? It will be constant. It's, so for example, like a system, and if there are no if net external force in the x direction is 0, right? So in that direction, space is going to be homogeneous, and of course, the x component of the total linear momentum in that direction is constant, right? So that's why I added the subscript I. Okay. So I will add probably in words. So this is the total linear momentum. So total linear momentum in which way I wrote in qi direction. Of course, if it is x, so it will be in the x direction. So y direction, and so on. Okay, so yes, basically the major point was here. First, we just apply some calculus, then apply homogeneity conditions of the fact that space is homogeneous, and as a result, immediately it led us to conservation of linear momentum. Right. Okay, so we connected conservation of linear momentum with homogeneity of space. Right. So now, next step naturally should be, actually maybe not so naturally, we use something which we did not prove, which we did not show, we even did not, no, probably justified, yes, right? Look, what we used. We used these things, that dl, partial derivative of L with respect to generalized coordinate, no, to generalized velocity, it's a linear momentum. But we didn't show it. Also, we didn't show that this dl over dq, partial derivative of L with respect to generalized coordinate, is a generalized force. But again, we didn't use it, we didn't show it. So let's sort of like these two gaps which we used, and now it's time to show them. Let's prove them, right? And then the case about the connection of angular momentum with isotropy of space we'll skip, right? You can read. And then proves that in this case, when coordinates are angular, the fact that this gives us torque and this gives us angular momentum will be in your homework. But I don't want you to waste tons of time getting through books. I usually provide the solution. You just need to read it, understand, and reproduce it by yourself. Right? So instead of me delivering it here, you can just read it by yourself and understand. So, but now back to showing that generalized force is a force and generalized momentum is linear momentum. Right. Now it's time for me to put a big bullet, right? And you know what? I probably need to write the summary. Right? I said in the words, but I didn't write the summary, right? And then I will put the bullet. So the homogeneity of space implies that the linear momentum remains constant through entire motion. So let's just write the conclusion, because otherwise there's no closure, right? So we need to. So so the homogeneity of space implies that the linear momentum remains constant, implies that the linear momentum remains constant or conserved. Constant throughout the entire motion, of course, right? Constant the entire motion. Okay, so now, yeah, I feel better. Because before without this conclusion, didn't feel well. Okay, so now back to the green bullet. And now let's show. Okay, so let me again state. So if Qi is a translational coordinate, then let's show okay, that Q, which subscript I use, Qj, yeah. It's a Qj component of the total force of the total force. Okay, that will be the first step. And the second step about a linear momentum, that generalized momentum is actually the corresponding component of the total linear momentum. Right. And Pj, again, it's again the same component of the total linear momentum. Because yeah, we used them, but we didn't show that. So probably I will write here, it's 1 and then 2. So let's start with 1. Definition of generalized force. You remember chapter 1 when we discussed, okay, not discussed, when we massaged, right, D'Alembert's principle, right, in order to rewrite it in terms of linearly independent coordinates, generalized coordinates, right? So we introduced that definition of generalized force. So let's just recall it. So subscript which? J. Okay, awesome. Qj equals summation over the whole system from 1 to which, okay, to n or n capital, right? So it's not a big deal. And that dot product actual force, right? Dotted with partial derivative of basically all coordinates which are which are linearly dependent to the linearly independent generalized coordinates, right? Wait, coordinates, not velocity. Right? So that was by definition. Okay, I will put 3 lines, and again, it's a chapter 1, from chapter 1. Actually, equation 149. Okay, let me write equation 149. So it's equation 149. Okay, so nothing to understand with the force. Force, you just introduce it, right? So since there are some interactions in your system, right? So we just need to understand what happens with this partial derivative. Old coordinates versus new coordinates. And of course, in order to make a transition from old coordinates, which are Cartesian, to new one, we usually introduce transformation equations, right? So again, from chapter 1, so let's recall transformation equations, right? So transformation equations, there are a few of them most of the time. So it's a Ri, a function of all these new coordinates and possible time dependence, right? Yeah. There's only one thing which kind of now I started looking and I'm not completely happy. I don't like this small n. It should be n capital, because n small, it's a number of here, number of generalized coordinates, and number of particles, n capital. So let me switch to n capital. First I thought it wouldn't be important, but now I realize that this number and number of particles are 2 different things, right? So we need to be careful, right? All right, and so now let's write explicitly this partial derivative. So it will be partial derivative of Ri with respect to Qj, right? Okay, from the point of view of calculus. So of course it's a limit, right? When this dqj goes to 0 and the ratio, these r's, Ri at qj plus dqj, okay, let me write j, right, minus, so it's a sort of like a final position after the displacement, and minus position before displacement, right? And of course divided by dqj. By definition, calculus, right? And now I'm just following the book basically, right? Explanation. So now let's draw a diagram of this, because now the key point is it's a partial derivative. So we're only changing this qj, basically only displacing the system along qj. The rest of the coordinates are fixed, are held constant, right? So let me draw the diagram in order to make that clear. Okay, I think I should be able to squeeze it here, yeah, although it will be difficult a little bit. Oops. All right, so let's say that, no, let me draw it a little bit lower. So this is qj direction, right? And maybe there's some unit vector in that direction, right? Let's call it n small, n hat. Might be difficult to see, but still visible. No, it's good. And so what this situation, so first the particle is here defined by this Ri qj, it's this vector, and then of course after the displacement, and of course as I said, we're only changing position in the QJ direction. The rest are held constant. So basically, it's a displacement along this axis, right? So it will be along this, right? And new position is defined by this, Ri, which is a function of Qj plus dQj. And so how can we write down this displacement? Of course, absolute value of that displacement, again, which is horizontal along the Qj direction. Absolute value is just dQj. Direction is determined by n hat. So this will be dQj times n hat. So this minus this is just a dQj times n hat. Now let me write this over here. So it will be dq sub j times n hat divided by dqj. And as a result, we have only, of course, this goes, we have only unit vector. Again, it's only in the case of a translational coordinate. So derivative of the partial derivative, very important, right? We're only treating qj as a variable. The rest are held constant, right? So this partial derivative of all coordinates with respect to the nu is just a unit vector in the corresponding direction, right? Okay, so now we can put it back over here. Let me. And yeah, I thought about squeezing everything on that side of the board, but I cannot. Right, I need to start erasing this. And yeah, I can erase this. Yeah, I don't need this. Everything can be erased. So as a result, Qj will be equal so Qj will be equal to what? Summation over the whole system and Fi dotted with n hat. Of course, n hat we can take outside, and of course, as a result, we have dot product with the total force. Did I label it somehow, the total force? No, just I left it like this, right? Because it's obvious, right? So this is the total force acting on the system. And then if you dot it with the direction, with unit vector along a certain direction, of course, it will just give us a component of the total force along that direction. And that's what we claimed from the very beginning. It's a component of the total force, right? In case of a translational, in case of a translational coordinate, of course, right? Okay, yeah. So how did I conclude? Oh, basically, right, so proved. So done. First part. This part, where is my first part? Yeah, this one. All right. So now let's take care of the second. So that will be 2. And okay, again, we claim that this partial derivative, right, is a generalized momentum. So let's use it. Let's write it. Pi. I think I use I subscript. Yeah. No, J. Okay, Pj. It's a partial derivative of L with respect to Qj dot. Right. Again, you remember we restricted ourselves to conservative system, right? Conservative systems, and we already used. I erased over here. No, I can see traces, right? So over here, we used typical Lagrange equation. And you remember, typical Lagrange equation can be used only if your system is conservative. So basically, even here, we restricted ourselves only to a conservative system or conservative system, right? So, conservative system, where you remember the main feature, of course, yes, that force is conservative, right? So we can introduce potential energy, and the potential energy is a function of coordinates only, no velocities. Those are monogenic systems, and we're not discussing them right now here, right? So V is the function of Qi's only, right? So the partial derivative of V with respect to Qj dot is 0. So dV over dQj dot is 0. As a result, I can write this as dT. T is the kinetic energy. Of course, total kinetic energy of the system, because we're talking about the Lagrangian, which describes the total system. Of course, it will be equal to partial derivative of T with respect to Qj dot. Right. Okay, so now let's write down explicitly kinetic energy. So it will be partial derivative with respect to Qj dot, and the total kinetic energy, summation over the whole system, 1 over 2 mi, and I think I used R. Yeah. Ri dot squared. Oh, conservation of brackets. Okay, so let's differentiate it with respect to Qj. Basically, this is dot product of two velocities, right? So we have to differentiate it properly. So 1, 2 will go, disappear. So we will have mi, then ri dot, and dotted with partial derivative of ri dot with respect to Qj dot. Here, nothing fancy, it's just a velocity, right? Nothing can be done with that. Let's take care of these partial derivatives. Again, it's what? Old velocities versus all new velocities, right? You remember, these are linearly dependent, these are linearly independent. And now, again, let's recall chapter 1. I told you in the chapter 1 that we're going to address those things a few times in this semester. Again, when we massage that D'Alembert's principle. And before we started massaging, I prepared 2 ingredients, I think I called them, right? And one of the ingredients was that this partial derivative of old velocities versus new velocities equals to the partial derivative of old coordinates versus new coordinates. And we proved it over there. So now let's just recall it. All right. Recall chapter 1 that a partial derivative of old velocities with respect to new velocities equals to the partial derivative of the old coordinate with respect to the new ones. And it's definitely time to change my marker. It's getting lighter and lighter and lighter. I need to get to the department to get more markers. The thing is, the new ones usually for the first like 15 minutes difficult to erase. I'm still struggling with blue color. Now I'm going to do this. I'm going to have the same with this black. Now it will be difficult to erase. Yeah. So yeah, we replaced this. I mean, yeah, showed, and now we just need to replace. So it will be summation mi ri dot dotted with now partial derivative of this with respect to q dot. And at this point, we can recycle results from the first part. That's why I started with generalized force, because we needed these results. You see, partial derivative of these old coordinates with respect to new is just a unit vector in the corresponding direction, in that direction. So this is just the unit vector, which gives us direction of qj. So let me show that this is equal to n hat. And as a result, we're getting almost close, very close to the end. So again, summation over the whole system, mi ri dotted with the unit vector n. Okay, so now we just need to move terms. Not it's dot disappeared. Basically, I should have switched to velocity. Okay, I will do it next. So it will be n hat dotted with summation mi vi, right? And yeah, over the whole system from 1 to n number of particles, of course. N small number of generalized coordinates, but n capital number of particles. So obviously total linear momentum of the system dotted with unit vector defining a certain direction. Of course, it will give us a component of the total linear momentum along that direction, for example, x direction. So this is, and guys, maybe if you didn't take undergraduate class with me, right? So whenever I write like P with the bar underneath, it means P capital, right? So it means that it's a total linear momentum of the whole system. Why I emphasize? Because I remember when I was taking classical mechanics graduate level, and professor, it was difficult to see the difference between P small and P capital, right? And every time you had to sit and decipher it. Of course, I have my own hiccups, like it's difficult to see the difference between U and N, but those are words. Symbols, we have to be a little bit more careful. So, n hat dotted with total linear momentum of the system. So, of course, it will give us a corresponding component. So, now conclusion, like there, because without conclusion, it's not good. So, Pj, okay, it's a small one, right? Is a component of the total linear momentum of course along qj direction. Right. Okay. So now, yeah, we proved what we used already several times. Right. It's not that crucial, right, in order to solve problems, but it's theoretical course, so we need to justify everything, prove everything. Right. So now, yeah, we connected linear momentum, conservation of linear momentum with homogeneity of space. We showed that generalized force is a regular force. Linear momentum, generalized momentum is a linear momentum. Now let's do the same for angular coordinates, right? And of course, and now, of course, which will lead to the conservation of angular momentum. So now, if a space is isotropic, isotropy of space leads to a conservation of angular momentum. Again, what does it mean, space isotropic? Let's say this is the axis of rotation, right? For example, z-axis. And we are talking about this angle, let's say phi angle. So if your system first here, right? If you let the system live here, of course it will live its some life, right? Then if you grab that system, freeze it so the conditions, initial conditions will be exactly the same, and turn it along this axis of rotation using this angle, and let it live here, you wouldn't be able to see the difference in the life of the system, in the motion of the system, right? Between system being here and there will be exactly the same. So in this case, we can say that space is isotropic. So basically, all very similar things will have to be done except for yeah, I used to do it, and then at a certain point I decided, yeah, it's I will skip it, except for only one major kind of difference, right? Where I varied Lagrangian, no, I erased it. Over here there was a variation of the Lagrangian. Okay, when we made a transition from straight DL to virtual DL, and there was a dq dot. So we had something like this, right? So we had dqj dot, right? And I told you in that case it was zero when you made a transition to virtual displacement, because upon virtual displacement, if first velocity was that way, if you displace it, velocity will be still the same way. So variation of that velocity will be zero. But when you rotate the system, first velocity was that way, okay, this way. If you rotate it, direction of the velocity changes. Of course, magnitude will be the same, but direction changes. As a result, variation of delta qj, q dot j is not going to be zero. So you have to take care of that, right? Of course, I'm not going to force you to do that. And if you want, you can read through the book. I just wanted to emphasize on this difference, right? Okay, so again, as I said, I used to derive it. It would take like 10 minutes, so but I decided to skip. So let me just write in words connection between isotropy of space and conservation of angular momentum, and then again this part where you will have to show that qj. Okay, if this is an angular coordinate, then qj it's a torque, and this is an angular momentum. You will do it in your homework, but again, as I said, I'll provide you my solutions, basically derivations. It will be attached to the homework. Your goal is just to read it by yourself and reproduce it. So it shouldn't be very time consuming. Okay, but let me write about okay, I will put probably the red bullet because it's now completely different, right? Switching from all this. So similarly can be shown that conservation of angular momentum, the conservation of angular momentum is a consequence oops, I messed up at the end, of isotropy of space. Okay, explanations of isotropy of space, I think that which I gave should be enough, right? So again, basically, since life of the system exactly the same, it means Lagrangian of the system over here and Lagrangian of the system after the rotation must be exactly the same. Again, you looked at the variation of the Lagrangian and see what you can get out of that mathematically. And then, of course, after a few iterations, a few moves, it will lead you to something similar. There will be some dot product giving us corresponding component of the angular momentum, which is constant, which is conserved. So what's in time? Okay, 5 minutes left. Awesome. So I guess, yeah, we will start now conservation of mechanical energy. And so we will start, and then next class, maybe like 10-15 minutes, maybe 10 minutes, and we will be able to finish it. And after this chapter will be over, and we will move to central forces. I just checked central forces. We will basically start discussing scattering. So we're almost ready to move away from the this mass. Okay, so I will erase this. So first, originally, you're trying to cover everything, and then after some time you think, maybe I'll skip this because this derivation and the next derivations are somewhat similar, so just trying to maybe be more efficient, right? Changes your opinion is evolving. So energy function and the conservation of energy. So it's still chapter 2. So energy function and conservation of energy and the conservation of energy. Okay. So again, let's assume that we have some system of n particles, right? And some Lagrangian, which describes behavior of that particle, okay, life of that particle. Again, it depends on generalized coordinates, generalized velocities. I runs from 1 to n. Okay, so these are generalized coordinates. So n, usually n small, defined number of generalized coordinates, right? So now, where should we go from this point in order to get conservation of energy? Who knows? So let's just for fun start looking at the dynamics of the Lagrangian. Let's see what happens with the Lagrangian in time. So let's just look at the total time derivative of the Lagrangian, hoping that it will lead us to somewhere. So dl over dt, just for fun, in a search for some troubles, right? dl over dt, of course, total time derivative, of course, time dependence almost possible everywhere. So we need to carefully differentiate it, right? So it will be summation over I think I used I. No, j. Okay. I don't want to change indices in terms of some troubles, then it will be easier to find where I made some mistakes. So partial derivative of L with respect to Qj, dQj over dt, maybe I should have written Q dot, but why not? Plus, again, summation over J, partial derivative of L with respect to Qj dot, and d over dt over Qj dot, right? And plus partial derivative of L with respect to t. Okay, that's all possible components, terms. Now, what else can be done? You know what? Let's use typical Lagrange equation in order to replace this. So of course it will be equal to d over dt and partial derivative of L with respect to Qj dot. So Lagrange equation. Immediately, when I use this, I'm immediately restricting our results to which case? If we use typical Lagrange equation, immediately we're restricting ourselves to a conservative systems only, right? Because typical Lagrange equation of this form only works when the system is conservative, right? Okay, so I will remind you about this in next class, right? So now let's just rewrite it. All right, okay, lots of rewriting, but that's the common problem of calculus. All right, so this I will write just Qj dot. Of course, this time derivative is not applied on that Qj dot, right? You understand? Then plus summation out of this. Okay, j and dQj dot over dt and plus dl over dt. Okay, so now, if we look carefully at these first two terms, we have total time derivative out of this function, and then this function's time total time derivative of that. It's a total time derivative of a product this times that, these two terms, right? I think it's obvious. So we can write it as, probably I will write, I'm just looking where should I put the summation sign. Okay, let me take it outside. It's not a big deal, right? Summation j, and so it will be d over dt, and the product of dl over dqj dot times qj dot. Okay, plus partial derivative with respect to time. So let me see. This will give me that term, and then to this, yeah, so that's correct. Okay, and the last step, I just want to get to energy function, and then we'll call it a day. So now, of course, summation can be taken inside. Now we have total time derivative here and total time derivative there. Okay, let's combine them. It's I think it's a natural move, right? Let's combine them because they have similar structure. So, and I will move this dl over dt to this side. So as a result, we will have d over dt, and since this goes to that side, it will be, this was plus, that was minus, so it will be summation qj dot dl over dqj dot minus Lagrangian, which came from here, and we still have plus partial derivative, this term like an orphan standing here all the time doing nothing, right? Okay, so now we introduced, we naturally, we haven't done anything except for just natural manipulations. We ended up with some new construction which we've never seen. First time in our life, let's call it this way, right? So let's give it a cool name. Maybe we can get something useful out of that. Next class we will massage this in order to extract what can be inside of that. Right now it's just a bunch of mass, right? So summation, of course, over j, okay, from 1 to n. So let's give it a cool name, energy function. All right, so let's call it h, right? So let me call h. Of course, it will be a function of q, which subscript I use? I here, okay, why not? qi dot t, and I will put 3 lines by definition, so that's how we define it. So summation over the whole system. Oops. Okay. Yeah, let me keep the same subscript, j. Right, j from 1 to n, and it will be qj dot partial derivative of L with respect to qj dot minus L. Energy function. Okay, I wanted to get to this point, and now we can move. I mean, call it a day. Energy function. Again, it's not energy yet. Again, right now it looks like some kind of mass. So, okay, it looks like on Thursday, because on Tuesday we're not going to have a class. We're going to look at that carefully to see under which conditions we can get energy. And also maybe like in a month or so, when we will go to Hamiltonian, very similar structure will be used to define Hamiltonian function. But the difference between energy function and the Hamiltonian function will be in only one small piece. Here it's a function of q dot, generalized coordinates, generalized velocities. In the Hamiltonian, there will be only q's and p's linear momentum. No. Otherwise, the structures are very similar. Okay, so from this point I will continue next class, right? And that's actually where I finished in the previous year.